Look closely at this generated video of a glass shattering. The lighting is photorealistic, the reflections are ray-traced with uncanny accuracy, and the fluid dynamics seem flawless. But watch what happens when we reverse the footage and analyze the center of mass. The shards don't converge to the original glass structure, they overlap, clip through each other, and violate the Pauli exclusion principle. This was the magic, and the inherent tragedy, of OpenAI's Sora. It was the undisputed king of generative video, yet it fundamentally did not understand the physical world. It was a master painter, blind to the laws of Newtonian mechanics. Sora astounded the world by generating 60 seconds of temporal consistency. It felt like we had achieved a world model. But there is a profound epistemological difference between dreaming a plausible sequence of pixels and simulating a causal universe. Sora dreams. It hallucinates correlations based on massive datasets. But as we push toward artificial general intelligence, correlation is no longer enough. We require causal, physical grounding. Today, we are saying goodbye to Sora, and dissecting the mathematical paradigm shift that is replacing it. To understand why Sora is becoming obsolete, we must trace the phylogenetic tree of generative models. In 2014, Generative Adversarial Networks, or GANs, introduced the concept of pitting two neural networks against each other. The generator created fakes, the discriminator caught them. GANs produced sharp images but suffered from mode collapse, failing to capture the full diversity of the data distribution. The underlying math was a minimax game, optimizing a Jensen-Shannon divergence that was notoriously unstable to train. Then came the diffusion revolution around 2020. Instead of adversarial training, diffusion models rely on non-equilibrium thermodynamics. They systematically destroy data by adding Gaussian noise over hundreds of steps, a process modeled by a forward stochastic differential equation. The neural network's job is simply to learn the reverse time process, to denoise. By learning the score function, which points toward regions of higher data density, diffusion models achieved unprecedented stability in diversity. This birthed Midjourney and DALL-E. But early diffusion models used UNets, which rely on convolutional neural networks. CNNs are highly localized, they struggle with global context. Enter the Diffusion Transformer, or DiT, the architectural backbone of Sora. In 2022, researchers replaced the UNet with a transformer. Transformers, originally designed for natural language, use self-attention mechanisms to weigh the importance of every part of the data against every other part, regardless of distance. When you combine the stable generative power of diffusion with the global routing capabilities of a transformer, you get Sora. Let us dive into the hardcore mechanics of Sora. Step 1, Compression. Operating directly on high-resolution video pixels is computationally intractable. Sora uses a variational autoencoder, or VAE, to compress the raw video tensor into a lower-dimensional latent space. A video with dimensions time, height, width, and color channels is squeezed into a dense geometric block. The encoder minimizes the Kullback-Leibler divergence between the encoded distribution and a standard Gaussian prior, forcing the network to extract only the most essential semantic features. Step 2, Patchification. Just as large language models break text into tokens, Sora breaks the latent video block into spacetime patches. Imagine slicing our 3D latent block into smaller cubes. Each cube contains both spatial and temporal information. These cubes are flattened into a 1D sequence of vectors. This is the stroke of genius that allows the transformer to process video exactly like it processes text. To the transformer, a dog running across the screen is just a sequence of spacetime tokens that need to be arranged in the correct order. Step 3, the denoising process. In training, extreme Gaussian noise is injected into these spacetime tokens. Sora's DiT backbone takes this noisy sequence, alongside text conditioning vectors from a clip model, and predicts the noise that was added. Mathematically, it is estimating the score, the gradient of the log probability density of the data. By subtracting this predicted noise step by step using Langevin dynamics, Sora sculpts a coherent video out of absolute mathematical chaos. But here lies the first fatal flaw of Sora, the computational wall. The self-attention mechanism in a transformer has a time complexity of $O, n squared, $, where n is the number of tokens. In text, n is a few thousand. In a 60-second high-definition video, n explodes into the millions. Every single spacetime patch must attend to every other patch across all frames. As resolution or duration increases, the compute required doesn't scale linearly, it scales quadratically. This is why generating a single minute of Sora footage requires staggering amounts of GPU cluster time. The second, more profound flaw is physical hallucination. Sora models the joint distribution of pixels across time, $p, x_1, x_2, x_t, It learns that if there is a shattered glass in frame 50, there should probably be an intact glass in frame 1. But it does not learn the differential equations of motion. It learns statistical correlation, not physical causation. When an object is occluded, or when multiple complex interactions occur, like fluid splashing against an irregular surface, the statistical approximation breaks down, resulting in objects morphing, disappearing, or defying gravity. To understand this deeply, we must look at the math. Diffusion models use score matching. They map a continuous noise distribution back to a data manifold. However, the physical world operates on Markovian state transitions, where the state at time $t plus $1 is strictly a function of the state at time $t plus some action, governed by the laws of physics. Sora doesn't compute $x_t plus 1 equals f, x_t, it denoys the entire spacetime volume simultaneously. It paints the future and the past at the exact same time. It is a spatial solver trying to fake a temporal universe. This realization is triggering a massive paradigm shift in AI research. If simultaneous spacetime denoising is computationally doomed and physically ungrounded, what is the alternative? The answer lies in returning to the roots of what made large language models so successful, autoregression. Instead of predicting noise across a whole video, next-generation models treat video exactly like a language. They predict the very next frame, or the very next token, given the history. This enforces strict temporal causality. The past dictates the future, just as time flows in reality. To make autoregressive video work, we need a different kind of compression. Enter models like Magvit v2. Instead of a continuous latent space used by Sora, these use a vector quantized variational autoencoder, or VQVAE. They compress video into discrete, finite tokens. Just as the English language has a finite vocabulary of words, a VQVAE creates a finite, visual vocabulary of spacetime dynamics. A specific token might represent edge moving left at 2 meters per second. Now, generating video is literally just next token prediction. In an autoregressive transformer, we apply a causal mask to the attention matrix. This is a lower triangular matrix of ones and zeros. It mathematically strictly forbids a token at time $t from looking at any token at time $t plus $1. It cannot see the future. This forces the model to learn the actual transition dynamics of the scene. If a ball is thrown, the model must deduce gravity and momentum to predict the next token, rather than just hallucinating a ball trajectory based on a global spacetime average. Causality is baked into the architecture. But autoregressive transformers face their own demon, the context window. To predict frame 1000 accurately, the model ideally needs to remember frame 1. But because of the $O(n²) attention complexity, keeping a long history is computationally suffocating. If a character walks out of a room and returns 5 minutes later, an autoregressive transformer might forget what they were wearing. This memory bottleneck is the primary reason why pure autoregressive video models haven't completely dominated yet. They are causal, but they are forgetful. This brings us to the bleeding edge of AI architecture, the true successor to the transformer, state space models, specifically Mamba. SSMs offer a dimensional strike against the context window problem. Instead of looking back at every single past token, an SSM compresses all historical information into a hidden state vector, $h_t$. When a new token arrives, the model updates this hidden state using a continuous time differential equation discretized for deep learning. It processes sequences with $O(n) linear time complexity, theoretically allowing for infinite context. Mamba achieves this through a hardware-aware algorithm called selective scan. It optimizes memory reads and writes directly at the SRAM level of the GPU, bypassing the slower HBM memory. It selectively decides what information to remember and what to forget. If a blank wall is generated for 10 seconds, Mamba ignores it. If a complex object is introduced, Mamba updates its hidden state. This allows for the generation of infinitely long, temporally consistent video streams without the quadratic compute penalty of Sora's DiT. However, Turing Award winner Yann LeCun argues that even autoregressive next token prediction is fundamentally flawed for video. Why? Because the physical world is infinitely detailed and largely unpredictable at the pixel level. If you try to predict the exact pixel values of rippling water, the sheer entropy will cause the model's loss function to explode. LeCun proposes that true world models should completely abandon predicting pixels. Instead, they should predict the future in an abstract representation space. This is the Joint-Embedding Predictive Architecture, or JEPA. In JEPA, you take the current frame, $x$, and a future frame, $y$. You encode both into a latent space. The model's task is not to generate the image of $y$. Instead, given the latent representation of $x$ and an action vector, it predicts the latent representation of $y$. By operating strictly in this abstract space, JEPA ignores irrelevant background noise, like the exact position of a leaf blowing in the wind, and focuses entirely on the causal dynamics of the core subjects. JEPA relies on energy-based models. Instead of outputting a single probability distribution, an energy-based model assigns a scalar energy value to a configuration of variables. Low energy means the configuration is physically plausible, high energy means it violates learned constraints. If a model predicts a glass moving through a solid table, the energy spikes. This framework allows the AI to learn the constraints of reality without needing to render every single photon. It learns the idea of physics. The future of video generation will not be pure diffusion, pure autoregression, or pure JEPA. It will be a hybrid. Imagine an architecture where a JEPA-style world model computes the causal, physics-accurate latent transitions using a Mamba state space backbone for infinite memory. Then, once the abstract physics are solved, a highly optimized diffusion decoder translates those latent states back into photorealistic pixels. Physics engine in the mind, diffusion painter for the canvas. Let's elevate this to the realm of information theory. Why is video so much harder than text? Text is a human invention, a highly compressed, low-entropy symbolic system designed specifically to convey meaning. Video is a raw, uncompressed capture of the universe's entropy. A single frame contains millions of pixels of largely irrelevant data. Sora tried to force-feed this raw entropy into an architecture designed for compressed symbols. It was a brute force attack on reality, and the compute scaling laws are finally showing their limits. Contrast this with how the human brain processes video. According to Carl Friston's free energy principle, the brain is a predictive engine. We do not passively absorb millions of pixels. We maintain an internal world model and only process the prediction errors, the sensory data that violates our expectations. This is active inference. We process reality in the latent space, just like JEPA. If AI is to achieve true understanding, it must stop trying to memorize the noise and start predicting the hidden states of the world. If next-generation models successfully learn the differential equations of reality from raw video, they will cease to be mere video generators. They will become universal simulators. A model that can perfectly predict the next state of a fluid dynamic system, a chemical reaction, or a biological cell, is essentially a generalized physics engine. This is the true goal of AI. Not to make pretty videos for social media, but to create in-silico laboratories where we can simulate the universe at a fraction of the computational cost. We are approaching a point where the concept of rendering might become obsolete. In traditional computer graphics, we build 3D geometry, apply textures, and calculate light bounces. It is a deterministic, top-down process. With true neural world models, rendering becomes a probabilistic inference task. We don't build the scene, we ask the network to sample from the distribution of all possible physically accurate realities. The video game engines of the 2030s will not be written in C++, they will be massive, real-time autoregressive latent spaces. So, when we say goodbye to Sora, we do not dismiss its monumental achievement. Sora was the Apollo 8 of generative video. It proved that we could leave orbit, that high-fidelity temporal consistency was possible. It forced the entire industry to scale up compute and rethink data pipelines. But just as Apollo 8 was a stepping stone to the moon landing, Sora's brute force diffusion is merely a stepping stone to causal, autoregressive world models. It showed us the illusion of reality, so that we could realize the necessity of simulating it. We stand at an epistemological horizon. For the first time in human history, we are teaching machines not just to recognize patterns, but to deduce the hidden laws governing those patterns. When a machine can watch 1,000,000 hours of video and independently derive Newton's laws of motion without human labeling, we will have crossed the threshold from machine learning to machine discovery. The pixels are just the interface, the physics is the prize. The era of pure spatial-temporal denoising is peaking. The future belongs to architectures that respect the arrow of time, that compress entropy into semantic latent spaces, and that prioritize causal constraints over statistical hallucination. Whether it is Mamba, JEPA, or a hybrid we haven't even named yet, the next breakthrough will not just look real. It will be fundamentally, mathematically grounded in reality. The dream is over. The simulation has begun. If you want to stay ahead of this paradigm shift and understand the hardcore math driving the future of artificial general intelligence, hit the subscribe button. We don't just cover the hype here, we deconstruct the underlying physics and code. Like this video, share it with fellow engineers and researchers, and let me know in the comments, do you think autoregression will solve the physics problem, or do we need an entirely new mathematical framework? Until next time.